Good evening, Professor and everyone. My name is Katara, and today I'm going to do a presentation on a paper which the title is CNN Sound Classification Mechanism Using Data Augmentation. So, this is going to talk a lot about data augmentation technique we use to enhance on the classification of CNN model. So, let's get into it together. And in this slide presentation, I'm going to divide all of that section into this point from introduction into the conclusion, and I will talk about some related work, proposed method, and also the experiment results as well. So first, we go to into the introduction. So I would like to cover up on the abstract section first. This paper is going to talk about the quality of training datasets, such as cost and resource constraints, data imbalance, and data annotation issues that cause the classification performance and being affected by all of this point. And this work proposed a sound classification mechanism based on CNN model, which is a convolutional neural network, and use sound feature extraction method of male frequency capture coefficient. We call it in short is MFCCS to convert the sound signal into spectrogram. Yes, so I will detail what the spectrogram will look like as well. And the dataset that being used in this experiment is ESC50 and the Urban Sound HK dataset. So to understand about this paper clearly, all you have to know is to identify some keywords which are sound classification, signal processing, and a little bit introduced to CNN model. So yes, I would like to clarify and divide it into the differences between sound and audio as well. So if we are talking about sound, the sound refers to physical vibration that travel through air and are detected by human ear, like us, and it is physical phenomenon that exists in nature. For example, you can hear someone clapping, you can hear me do the presentation or anything else. If we want to talk about the audio, it is not too much different from the sound about. It is referred to electronic representation or recording of the sound. It is how sound is captured, stored or playback in electronic system. And I also have an example as well. So we can say that the sound that is being recorded is called audio. So when you listen to music on your phone, you will listen to my presentation on your laptop or computer. The music you hear, the presentation sound that you hear is the audio recording of sound. So it converts into digital signal to be able to play back like you are watching. And the application of sound classification, it is complex, feature-rich signal, and receiving is strong, interested in a growing number of application areas such as speech recognition, music analysis and recommendation, environmental sound monitoring, anomaly detection and security, and sound classification methods rely on signal pre-processing technique that involve so many steps to extract relevant feature and classify sound signal. So you have know what is the sound and audio, the difference between two of them. So now let's get into what make the sound classification hard or the challenge in this section. The traditional sound classification method, they initially ran the unprocessed sound signal, which is electronical capture, and the audio signal are pre-processed by eliminating noise, normalizing the amplitudes, and segmenting into smaller frame. So, and after that process, The feature extraction is performed by analyzing the frequency content of each of the smaller frame to identify and be able to classify what is it or what type of the sound come from. And this challenge is associated with cost and resource constraint, which emphasize the time, expertise, and equipment needed for collecting and annotating sound data. And also the data imbalance as well. It is uh, it can explain how uneven representation of different sound classes can affect model performance, and also the data annotation challenges. We will discuss they discuss about the subjectivity and potential error involved in manually labeling sound data. So let's get into the related work. So for the related work that some of the paper have been studied, they do the pre-processing. Audio signal are initially pre-processed to remove noise, like the traditional method as well. They normalize amplitude and segment the signal into smaller frame. And for the feature extraction, the frequency content of each frame is analyzed using technique like Fourier transform or short time Fourier transform (FT). This leads to frequency domain representation that can further process to extract features such as spectral energy, spectral centroid, spectral roll-off, zero crossing rate, and also the time domain statistical method as well. And the classification that extract feature are then used to train a classifier, often based on statistical model like hidden Markov model, HMMS, or Gaussian mixture model. And the limitation of the existing traditional method is, while this method rely on carefully feature engineering and domain expertise, they may face limitation in handling complex pattern or generalizing to unseen data compared to deep learning technique. So this means that if the if the sound that being captured and transformed into the audio, and the pattern of those audio digital signal is complex, they could not be classified, and also it could not be compared with the deep learning technique as well, because they can learn more better than this existing traditional method. So the author proposed a new method which is use CNN model and highly improved on the data augmentation technique. So this proposed sound classification mechanism include three main parts. So the first part is in here, data pre-processing, and then data augmentation. Yes, in here, and followed by the CNN classification model, which is used between this, and then they get the output. So let's get into the first part of data pre-processing. The goal of data pre-processing here is to transform the raw sound signal into a suitable input format for the CNN model. So to get the CNN model be able to do the training and testing, we will need to data pre-processing to convert the raw sound of signal into suitable input format. So the format is spectrogram of sound signal. As we can see here, after we convert it, we can see, and we can see the frequency that highlight in this spectrogram right here. So we will do the reading on how we can interpret this spectrogram of sound signal. You will need to know about the frequency as well. So the lower frequency are at the bottom of this spectrogram, and the higher are considered near the top, like this. it is corresponding to the pitch of sound. So by recording or making sound from time to time, specific time frame, we can have a time to show frequency of a sound signal change over a period of time. So in this representation figure right here, we have the x-axis which represent the time, and also the y-axis represent the frequency. So the amplitude that you can see here, so that the color or brightness represent the amplitude of frequency at a given point of time, and the more brighter of color represent louder, which means the volume is up. And then while the dark color indicate quieter or lower amplitude, which is in lower sound or lower volume. As we can see here, if we see the speech or the audio signal that we get from and representing to this spectrogram sound signal, all of the dark, the more dark it is, mean that the more louder sound. Yes. And if you don't see anything here, it is just a blank or some noise that we recorded from the sound. So now you understand how to interpret the spectrogram of sound signal. Let's go into the data preprocessing. So this is going to we will go through this step together. So the purpose of this step is to convert raw sound signal into spectrogram, as I have mentioned in the previous slide, which is a virtual representation of signal frequency over time. Yes, we can see it when the time change, the frequency and the amplitude also change as well. So we will use all those and break into this smaller chunk, and we can divide into short segmentation. We call it frame. So it is easier to study. And the author add some technique called pre-emphasize high frequency, which are used to improve their visibility in the spectrogram. So if it is too little frequency or low frequency, we will be able to identify it as well. If the color is too light or the level of shade is too low, we are hard to see that color. So that's why the author emphasize by boosting the frequency from low to high. It's easy to improve the visibility in the spectrogram, so that we can look into it. And the smooth transition between frame. So from frame to frame, a Hamming window is applied to reduce abrupt change at the end of each frame. And convert to frequency domain, as they use the FFT, is a fast Fourier transform that used to convert each frame that is already both from time domain to frequency domain, and apply the MEL filter, which I have mentioned in the first proposed method. The frequency spectrum is filtered using a set of triangular bandpass filter based on the MEL scale. So if you are interested in this augmentation session, this is very interesting. They filter some noise to get the identifier or classification more smooth. So it is the resemble human perception of pitch, and could get a result in a representation of signal energy distribution across different frequency bands. And then they extract the MFCC by using the discrete cosine transform DCT is applied to the output of male filter above and produce the male frequency capture coefficient, and then those extract MFCC will represent the spectral, which envelope of the sound and capture the most important feature of the classification. After then, the data pre-processing is and the role or the job of data augmentation will come. So this is used to apply, and the purpose is to increase the size of diversity of the training data set, which will help to improve the performance and generalization ability of the proposed CNN model. And the source focus on a data augmentation method using the map filter. Yes, I have told you it is very important. They use some technique like rational, the limited availability of training data. So why they use this male filter based augmentation? Because by rotationally the availability of training data is limited, as mentioned in the challenge section of sound classification previously as well, which can hinder the model performance. And the data augmentation address this by creating variation of existing data point. So they use this male filter based augmentation. The number of triangular bandpass filter used in the male filter state is varied using different set of filter from 20 to 25 increased by 5 until it's 40 filter on the same sound signal. So for example, if I have one of the original sound signal, if I apply the different set of filter, I will get a multiplied version of this following number. So we can say that it is the same sound but in different version. Yes. And this will produce multiple or similar sound, like I have told you, but not identical. Spectrogram from a signal, the sound list the set and corresponding number of filter used in this table below. So when the number of triangular band pass filter they use like this 40, it will represent the with the k value of 1. And when they use this set of triangular band pass filter like this followed by this, we can only when in further slide I will the author will use only this representation to represent this value from k1 to k value equal to 5. So let's move to the interesting part of how they construct the CNN architecture. The sound classification model is a learning model using CNN, as shown in the figure 2 below. The image after pre-processing of data is set to, after this, go into the input shape. If you set into 40 multiplied by 173 pixel as the input of input layer. So let's get into each of the three main part of this sound classification model. The first one is convolutional layer. This model has 3 layers of convolutional, which responsible for extracting the feature from input spectrogram that we get from the this input shape, data pre-processing and augmentation. So the convolution 1 will use 64 convolution kernel of size of this size, and followed by convolutional 2 using this amount, 3 using this amount of convolutional kernel. So when they use this to extract the feature from the input spectrogram, it can then go to the next step, which consists of two flattening layer. So what is the job of these two flattening layer do? So each node of this flattening layer will form into fully connected layer. We used to form a classifier, which means that the feature data that obtained through convolutional processes in here will be converted into corresponding output classification result. So we can say that it's a translator of classification result. And then after that we can get the output. So what is that sound? What type of that sound? And also the category. And next we go into the experiment result. So the experiment setup, they use this following hyperparameter. So I'm not going to read this. You can see it on the screen right here. And they will use, to remind you again, they will use two datasets. The experiment result based on ESC50 dataset, the first one. The setting of each procedure for data preprocessing are described as follow. So they will do like this with the limit. But I want to point out that this dataset has also limited the data size with only 40 samples per class. So it is very little. So they split into training. Yes. Please wait a bit. Yes. So the 40 here, which represent the original dataset that you see, they only have 40 samples per class. So it is the original of k equal to 1. Yes. And then they split the data into training by this 81 validation 9 and testing 10 set. And here is the 5 major category. The first one is animal, followed by this, and this. So the total is 50 semantic class across the 5 major category. And the experiment result of training and validation right here. The first one is referred to the k value equal to 1, and followed by the second figure will use the k value equal to 2. So it means that the original of data that has only 40 examples per class like this is for the k equal to 1. So when as you can see here, the training and validation graph, the accuracy is not closer to each other. So it's not having a good result. So, and then they also try to prove that the data augmentation technique is really help and enhance the model training and validation accuracy. As you can see here, both of these legend label are really close to each other. So only by increasing the k value to 2, so it will get more of the example per class. Yes. So because it is very similar to each other, they can only represent the k value to 2. And then the result of this, use the computation metric to show the actual predict on the dataset, or the original dataset. We can have k to 1. Each of the category, you can see the value of here can identify or classify the category of sound in very low amount. And if you see the augmentation by increasing k to 2 to increase the example per class, we can get a better amount of classification right here. So 1 to 5 is the major category, to remind you again. And this is another figure that, oh sorry, another table that doing the indicator for each category of sound classification. So for accuracy, precision, recall, and F1 score, we can see that the K value to 2 get all better in 4 of these metric. As you can see here, comparing to this side, it is below 0.70, so it is more than 0.70, so which means the technique of augmentation by increasing the example per class of case equal to 2 is better. And then they construct all of the K value from 1 to 5. As you can see here, only when we increase and when the dataset we use is lake of example, like in the K value to 1 for this blue dot right here, the accuracy result is very low. When they also increase the K amount of example per class to 5, they get most of the accuracy. We can say it is almost below 90 and up to 100 percentages. It is really good. So not only the accuracy, also the precision is better in the K value to 5, as you can see here. So I will be quick in this because it is all similar, recall as well, and also the F1 score. So we can say that when we increase the K value, have the dataset have more example per class, the result will be better. And then we can say the data augmentation technique really matter and matter to the model performance. And yes, the author is going to show us about the training experiment result based on another dataset called Urban Sound HK dataset. So in this dataset, we are not lacking of the example anymore. We have more than 8,000 labels of the urban sound from not only 5 classes but 10 classes. So it is a very big amount of data. So it's not limited as like before. So each sub is 5 seconds long. So we can extract to get the most of the frequency and fit into the CNN model to get the identifier or classification process more better. And this dataset is, like I have said, has a like amount with a sufficient number of example per class. So we get different classes with a different amount of data and the number of data in each of the classes right here. So without any further delay, let's get into the point of training and validation with this new dataset. The result here show that data augmentation method can only slightly increase the classification accuracy by 2 percentages compared with the original dataset when original dataset has sufficient data. So this is also the key point, key finding from the author that he want to mention. So if the dataset that we have is sufficient, we can say we do not need the increasement of example per class of the category anymore. As you can see here, the left one of A figure is the original dataset, and the right one, which is section in B, use the amplifying the amount of data by 100%, which use k value to 2. And they want to say that the accuracy is that getting better from the original one is only 2 percentages. So it's not really high comparing to the previous dataset. And as we can see here, the average of accuracy until the F1 score right here, the value of each of these metrics are not dramatically increased. So as they have said, this in this evaluation indicator as well. From the very first training and validation with the original dataset, they can get an interesting amount of accuracy as well, over 90 percentages. So it is already good with the sufficient dataset. And followed by this evaluation indicator. So when the author found out that when we have a sufficient amount of data, it is almost get a better result. So the author decided to prove that, and he will slide data into half for each of category and extract that is extract from the urban sound 4K. So divide dataset into half, and they use their amplifier the amount of dataset technique from increasing value from k to 2 to 5 to prove that. So they are not using the 100% of original dataset anymore, only use half. And the data augmentation mechanism with k value to 2 was used to generate a new training set with the data size. So when we extract to half, we will get this amount, and applying to the increasement of 100 percentages, this is equal to this multiplied by 2 equal to this amount. And we can see the sound classification result using this new training dataset is getting better. The training we get and the validation as well. And here is the evaluation metric, which consists of accuracy, precision, recall, and F1 score on the new dataset that they have the dataset into 2 and double it by using the data augmentation technique. Increase the k value to 2, so they get all better result in each of the category of evaluation metric, as you can see here. And then when they try to prove with the new training dataset, I mean on the same urban sound HK, but after they divide it to 2, the result of k value to 1 of original dataset are not good anymore. And when we use data augmentation by increasing the k value, and the dataset will be amplified, and the amount of data, example in class in each category is increased, so that the result of accuracy here is increasing better. Yes. So when the k value equal to 5, the accuracy is already reached to the 97 percentages, while the other accuracy of another proposed method are below 90 percentages. So you can say when we train this model, we can use data augmentation technique to enhance our data quality, so that we can get a better model performance. So in conclusion, evaluation indicator summary. The study focused on evaluating their mechanism on two datasets. This one is very limited, and another one is very sufficient dataset. And they investigate the sound classification mechanism using CNN model and apply mainly on the data augmentation method to see the enhance on the model performance, and particularly when dealing with limited training dataset, right, ESC50. And the key finding from the study is the effective of data augmentation. So I don't want to read this anymore, as I have explained all the in all the experiment results already. When we have small amount of data per class, we should do the data augmentation to boost or enhance or to get the larger amount of example per class to get the training and validating in better accuracy. And the limited impact of data augmentation is really low for a very sufficient dataset like urban sound HK. When we see the technique before half sliding the original dataset of urban sound HK into 2, the result of applying data augmentation from k value 2 to 5 is not increasingly very increasingly in different gap of the value or accuracy. So they say that their technique is really good. We don't have to use all the original of urban sound HK. So they slide it into half, which means it is reduced by 50 percentages of the original dataset, and then they apply the data augmentation, which allow model to achieve a high accuracy of over 90 percentages. And after this, the author emphasized that data augmentation method inherently address the issue of data imbalance by generating multiple versions of similar spectrogram from the same sound of data. This will help to balance the representation of different classes during the training. So I can say, if you want to identify human sounds, you will so human sound that come from different region or country. If you only have the data set of human sound from for example from only 10 countries, you want to classify the sound where this original sound of this human come from which country, you won't get a better classification result. You will need to have more data set than this. So this is what the author trying to say. And even if we are in the same country, we also have different tune or sound as well. So that's why it's very important. It is coming to the end. So the author also point out their future research direction as well. The source acknowledge that real-world classification tasks often involve factors like environmental noise influences and overlapping sound, which can impact the model performance. So the sound that they have tested before are not overlapping. So imagine if you are going to use this model into the real environment, so how can they remove those, we can say it's noise, to the original dataset? So this is the way to improve the future work. And for the future research, they will focus on refining data augmentation method to address this challenge. and improve the robustness of sound classification system in practical application. So this is all from me. Thank you so much for your listening. Thank you.